Hey everyone, and welcome to today's Explainer. I'm going to be your personal tutor today, and we're tackling Topic 3.1, Computer Architecture. We're breaking down all those tricky technical concepts from your syllabus, step by step, and throwing in the exact exam tips you need to maximize your marks. So grab a pen, and let's get into it. Here's our roadmap for today. We'll start with the von Neumann blueprint, look inside the CPU at registers and system buses, walk through the Fetch-Decode-Execute cycle, talk CPU performance, and finish up with instruction sets and embedded systems. All right, Section 1, the von Neumann blueprint. Let's start right at the foundational blueprint of all modern computers. So before John von Neumann had his light bulb moment in the mid-1940s, computers were incredibly tedious. You practically had to physically rewire them just to run a new calculation. But his architecture brought in this massive game changer called the stored program concept. Basically, it allowed the CPU to directly access memory where both the data and the instructions are stored together. It literally changed everything. To really wrap your head around this, it helps to think of the CPU as a highly organized factory. The control unit, or CU, well, that's your factory manager, reading instructions and sending out signals to keep data flowing smoothly. Then there's the arithmetic and logic unit, the ALU. That's your heavy machinery, doing the actual math and logic. And finally, the system clock. Think of it like a metronome, ticking away, keeping every single operation perfectly in sync. Moving on to Section 2, inside the CPU, registers. Let's zoom in and actually meet the workers on this factory floor. Registers are these super fast, tiny, temporary memory locations built right into the CPU. Honestly, you might want to take a screenshot of this cheat sheet right now, because you absolutely have to know these 5 specific purpose registers for your exam. Okay, so the program counter, or PC, tracks the exact address of the next instruction. The memory address register, the MAR, holds the address being read from or written to right now. The memory data register, the MDR, is like a buffer, holding the actual data going in or out. The current instruction register, the CIR, holds the instruction that's currently being decoded. And lastly, we have the accumulator, or the ACC. And speaking of the accumulator, here is a massive exam tip for you. If a question asks where temporary arithmetic values go, remember, the accumulator is the ALU's best friend. Examiners are actively looking for you to explicitly state that the ACC holds data temporarily during calculations. Write that down. Okay, Section 3, System Buses Data Pathways. We've got all of these registers, but how do they actually talk to the memory? They use system buses. Think of buses as parallel digital highways where every single wire carries one bit of data. There are 3 main ones you need to commit to memory: the address bus, the data bus, and the control bus. Together, they make up the overall system bus. Now, here is where it gets really interesting. Look at the directionality here. The address bus is strictly unidirectional. It only goes one way, outward from the CPU to the memory to find an address. The data bus, though, that's bidirectional. It has to go both ways because the CPU is fetching data from memory, but also writing process data back out to memory or to external devices. Oh, and the control bus is also bidirectional, sending management signals back and forth. Time for another golden exam tip. Examiners literally love testing to see if you know the address bus is unidirectional. Why? Because you absolutely don't want addresses being accidentally sent back into the CPU. Writing address bus is unidirectional is pretty much a guaranteed point on any architecture question. Take the easy points, guys. Section 4, the Fetch-Decode-Execute cycle. Let's actually watch this factory in action. This cycle brilliantly illustrates the exact step-by-step logic of how the CPU and memory interact. First, the program counter sends the address of the next instruction down the address bus to the MAR. Second, the CPU finds that address in memory, grabs the instruction, and sends it back down the data bus to the MDR. Third, that instruction is copied over to the CIR. Fourth, and don't forget this step, the program counter increments by 1, basically pointing to the next instruction so it's ready for the next round. Fifth, the control unit decodes the instruction. And finally, step 6, the instruction is executed via control signals. So, quick question. What happens if that decoded instruction tells the computer it actually needs to do some math, like adding 2 numbers together? Well, that is exactly when the arithmetic and logic unit wakes up. The ALU steps in during the execution phase to do the math, and it relies heavily on our trusty accumulator to temporarily hold those calculation values while it's working. See how it all connects? Right, Section 5, CPU performance factors. We know how the cycle works, but how do we make it go faster? Increasing the bus width helps, sure, but your big 3 performance boosters are clock speed, cache, and cores. Clock speed dictates how many of those fetch-decode-execute cycles happen per second. Cache is this super fast memory tucked right inside the CPU. It holds frequently used data so the CPU doesn't have to waste time reaching all the way out to your slower RAM. And cores? Well, a single core has its own ALU, CU, and registers. Adding multiple cores, like a dual or quad-core processor, lets the computer process multiple instructions at the exact same time. But hey, trick question alert. Doubling the cores doesn't perfectly double your speed because the CPU has to spend some time managing the internal communication between all those cores. To put clock speed into perspective for you, a typical modern CPU might run at 3.5 gigahertz. That equates to a mind-blowing 3.5 billion synchronized clock cycles happening every single second. Crazy, right? But listen, you can't just crank that dial up to infinity. Here's another huge exam tip. If they ask about overclocking in the BIOS, which is basically forcing the clock speed higher than it was designed for, you have to mention the downsides. Pushing it past its limits causes unsynchronized operations. Basically, instructions start crashing into each other before they can finish. This leads to severe overheating, system instability, and your computer will frequently crash. Finally, Section 6, Instruction Sets and Embedded Systems. Let's see how this hardware powers actual software and devices. Look, every single piece of software, no matter how complex, eventually boils down to an instruction set. It's just a limited, specific list of commands that a particular CPU hardware actually understands. In machine code, these commands have an opcode, which tells the CPU what to do, like add or load, and an operand, which is the data or the memory address it needs to act upon. Now, when you take this whole von Neumann architecture, shrink it way down, and purpose-build it for one specific task inside a larger device, you get an embedded system. These guys don't need big, clunky operating systems. They're microcontrollers running things like the timer on your microwave, the anti-lock brakes in your car, or the smart sensors in your house. So I'm going to leave you with this provocative thought to really test your understanding. Based on everything we just covered about architecture and performance, how would you design an embedded system for a simple supermarket barcode scanner? Do you really need a massive, expensive quad-core processor? Or would a single-core processor with a highly optimized instruction set and efficient cache memory do the job perfectly without wasting money or overheating? Think about matching the hardware to the task. Anyway, thanks for hanging out with me on this explainer. Keep reviewing those register definitions, don't forget your bus directions, and good luck crushing that computer architecture exam.